Hi, folks. In this next lesson, we're going to focus on accuracy and precision. These two words are often confused by students, but they do have separate, distinct meanings, and this is especially important when you're dealing with science. This picture illustrates the difference between accuracy and precision. This picture shows shots on a target. These shots are both accurate and precise. Um, Accuracy is how close measurements are to a true value. In this case, the bullseye represents the true value. And precise means how repeatable a measurement is, how closely clustered measurements are together. And here you can see all four shots are tightly clustered together. In this first bullseye, shows shots that are neither accurate nor precise. Not accurate, not precise. First of all, these shots are not near the bullseye. If look at kind of the average shot is way over here in the top left corner. So they're not accurate because they're not near the bullseye. And they're not precise because they're not close together. These are not repeatable measurements. We're not getting the same thing over and over again. The top right-hand corner shows shots that are accurate but not precise. Um, Students sometimes have difficulty seeing this. Again, accuracy is kind of like on average, are you kind of hitting the target? And you can see that the kind of average is over here. So like on average, we're hitting the bullseye. But the measurements, the shots are not precise because they're still all spread out. They're not clustered tightly together. This bottom left picture shows results that are precise but not accurate. They're clustered closely together, but they aren't actually close to where they're supposed to be. So hopefully this kind of gives you an idea of what accuracy versus precision is. In terms of measurement, generally, precision is indicated in measurements with how many decimal points a number is reported to. So if you say that somebody is 5 feet tall versus 5.1 feet tall versus 5.092 feet tall, this third number is given with much more precision. And if you're reporting that kind of precise number, the assumption is that you made the measurements very carefully. You used a high quality, precise measuring instrument. Otherwise, you wouldn't report a number with that many decimal places. And I've mentioned this in previous lessons, but this time we're going to officially learn it in this lesson. Your answer should reflect the precision that you see in the measurements that go into the problem. So your final answer should not be more precise than the numbers that went into the problem when you're working on real world math problems. That means you're not writing down every number just because you see it on the calculator. Okay, you need to make a judgment call based off of the context of the problem, writing down a sensible number of digits. So let's look at an example here. You use a centimeter ruler to measure the dimensions of a jewelry box. 22.5 centimeters for the length. The width is 11.3 centimeters. The height is 6.5 centimeters. And remember, volume, which is what we're being asked to calculate, of a box is one of those equations that you should know that we reviewed in the first section of this chapter. So volume is length times width times height. And if we want to calculate that, we're doing 22.5 times 11.3 times 6.5. If we plug that multiplication problem into our calculator gives us the answer 1,652.625. What should we do for units? If we have centimeters times centimeters times centimeters, our answer should be reported in centimeters cubed. Now, if you give me this final answer on a test, I will take off partial credit because it's not reported to a sensible number of decimal places. So let's look at what would be a sensible answer. This first value has 3 non-zero digits in it. This has 3 non-zero digits. This has 2 non-zero digits. So, one way to kind of view this answer is to kind of round off to, um, since most of the measurements have three non-zero digits, kind of rounding off to three non-zero digits here and saying 1,650. Um, Notice, because this is less than 5, we keep the number before the cutoff point as is. If this number in this place were 5 or higher, I would have rounded the 5 up to a 6. Notice also that I don't just chop the number off. I don't say 165. This one is in the thousands place. I need to fill in with zeros to keep that one in the thousands place. So 1,650 cubic centimeters would be a good answer. Um, Sometimes it's more appropriate to match the number of decimal places. Um, there are more specific rules that we use in science to count sig figs and track sig figs in problems. This textbook does not go into that level of detail that you may go into in your science classes. And so in my class, I would accept if you're like, well, they all my numbers have one decimal place. So if you chose to round off your answer here instead and said 1,652.6 centimeters cubed, I would accept that as an answer as well. So kind of anything in this range. Another possibility would be rounding off here and saying 1,653, yes, cubic centimeters. So any of those three are reasonable according to the rules outlined in this chapter of your textbook. But I definitely would not want to see 3 decimal places in your final answer. Let's look at this example. The population of the US in 2018 was about this big number in the millions. The national debt in 2018 was this gigantic number in the trillions. Estimate the US national debt per capita, per person. So, what this question is asking me to do is to calculate a rate with money or debt on top and divide by the number of people, the population. And remember, a rate is just a division problem where the numerator and the denominator have different units. So I'm going to have money divided by people. If we use the numbers as shown, 21,867,237,827,643 divided by 328,182,510, then you get the answer $66,631.332. Now, what level of precision makes sense in this answer? Well, population is constantly changing. People are dying, being born every moment. And certainly across the course of an entire year, you're going to need to have a wide variety of population in the population. The same thing is true with the national debt. The debt is changing every moment, every second. And therefore, you can't possibly say what the national debt was in a year with any degree of specificity. Therefore, it doesn't make sense to record your answer to the decimal, to the cent, even to the dollar or the tens of dollars, or maybe even the hundreds of dollars. Just kind of rounding this off at 67,000. Notice that if the dividing line here with this number after the dividing line being greater than 5 or greater, then this 6 here gets bumped up to a 7. And notice that we do fill in with the trailing zeros to make sure that our starting value, that very first 6, stays in the 10,000s place. It is a little bit arbitrary. If you wanted to say 66,600 per person, that seems like a valid answer as well. But knowing it to the tens, the ones place, is not reasonable. Another strategy you can use here is to round up off the values to begin with. There's no need to punch in such a precise number when that number is not actually known precisely. Um, so saying, oh, this is about 22 trillion divided by about 330 million. And then that, if you punch that into your calculator, you get 66,666.667. Now, in this case, because we only have two significant figures that aren't zero, here it definitely makes sense to round this number off to just two non-zero values. So saying 67,000. If you choose to round off your number, your debt and your population before doing the division, sticking with the same number of non-zero digits makes sense. So you get very similar answers with whichever strategy you use. It's obviously very convenient to not plug in quite so many digits into your calculator if it's not necessary. Let's look at one more example about how many 1-ton bags of mulch are needed to cover a 40.5 foot by 66.75 foot playground with mulch, and the mulch should be 0.6 inches deep. I have a very long and fairly wide playground that I'm trying to cover 6 inches deep. So this is a very shallow box, but it is box shaped. It's a rectangular prism where this dimension is maybe 40.5 and this is 66.75. But the depth, now I do want to match units here. This is measured in feet. This is measured in feet. So I'd like to convert that 6 inches to feet. 6 inches, remember, is half a foot. It's 0.5 feet because there are 12 inches in a foot. So I'm going to label the height of my rectangular prism here with 0.5. Hopefully you remember from the first section of this chapter that volume of our rectangular prism is length times width times height. So this would be 40.5 times 66.75 times 0.5. And if you multiply all those numbers together, you get 1,351.6875. Now, first of all, let's talk about units. This is feet times feet times feet. Therefore, my final answer here is cubic feet. And if this were actually the end of the problem, if this were my final answer, I would want to round this off to a sensible number of significant figures. There's no way I can know this so precisely when each of my measurements were just one decimal place. However, this is not my final answer. I want my final answer to be in 1-ton bags of mulch. And a 1-ton bag of mulch contains 81 cubic feet. So 1 ton is 81 cubic feet, or 81 cubic feet is 1 ton. I need to use one of those conversion factors to kind of take this number and convert it into bags of mulch. And then once I have that final answer, then I'll round it to a sensible number of significant figures. Looking at this, I want to choose the conversion factor that gets rid of cubic feet and converts to tons. So if I multiply this number by 1 ton over 81 cubic feet, the cubic feet disappear because they got divided away, and cubic feet divided by cubic feet is just no units. And so the only units I have left are these tons. And that's what I want to convert to. So if I do this multiplication problem, 1,351.6875 times 1 divided by 81 gives 16.6875 tons. Now, let's round this off to a sensible number of significant figures. Not only do I have to think about the measurements involved, so I wouldn't want to have more than one decimal place in my final answer, but does one decimal place in my final answer make sense? Does it make sense to say I'm going to buy 16.7, kind of rounding off here, 1 ton bags of mulch? I bet I can't buy 0.7 of a ton bag of mulch. I probably have to buy an entire 1 ton bag. So in this example, based off of the context of the problem, rounding off here makes more sense. So I'm going to go back to this value. This is a 6. It's greater than 5 or greater, so I'm going to have to round this 6 up to a 7. And I've got 17 tons of mulch that I need to purchase. So this real world problem does a good job of combining both those conversion factors that we learned about in the last section with rounding to a sensible number of significant figures given the context of the problem. I hope this helped.